Back to the classroom. My name is Mr. Wong. Today we're going to be covering inquiry question or module 3, inquiry question 5, thermodynamics. And we're going to look at the concept of latent heat. Now in the previous upload we actually talked about a concept called specific heat capacity. Now we're going to talk about latent heat because it matches in really nicely in that concept. Now we know with the three well-known states of matter, solid, liquid, and gas. We know that by increasing the temperature of a solid, it causes it to melt. We get a liquid. If that increases in temperature, it evaporates and we get gas. The reverse is true. If we decrease temperature, condenses into liquid and then freezes into a solid. Now in all this process, energy is being used to allow for these transitions to occur. And these are called latent heat. Okay, so you have latent heat of fusion from solid to liquid and latent heat from liquid to gas in terms of vaporization. Alright, so let's actually look at where we can identify that on a temperature heat graph or a temperature time graph. We already said before that the gradient of such graphs will tell you the specific heat capacity of that specific state. Okay, so solid and gaseous form of water has a steep gradient, meaning by it has a lower heat capacity, while as water has a higher heat capacity than the two of them. You can see in the transition from ice to liquid water, there is a 0 increase in temperature and also a 0 increase in temperature when we transition from liquid water to steam. Now the reason for that is, instead of energy being increased to make the molecules move or vibrate more, energy is now being used to separate the bonds. So that's why we don't see a change in temperature. There is no increase in translational kinetic energy. The energy now is causing the molecules to vibrate faster in order for them to separate from each other. So let's have a look. First one, latent heat of fusion. This is where we increase the energy of vibrations between these molecules, and that causes them to increase the average separation between these particles. So it causes them to weaken the attraction force between the molecules or between the atoms, causing it to move away from each other. And this transition is called latent heat of fusion. Latent heat of vaporization is where we have a complete breakage of any intermolecular bonds between particles. So once transitions in or transition to the gas state, the particles will spread away from each other. So let's say, for example, our little diagram here. If we've reached vaporization, we essentially see the particles move away in all random directions away from each other, and they will not attract back to each other, unless obviously we decrease the temperature. Okay, so keep in mind there's two types of latent heat we're going to talk about, and this is sort of how we define it. So the latent heat of fusion is the energy to shift 1 kilogram of substance from a solid to a liquid state without a change in temperature. The design is to increase the separation of the molecules. The latent heat of vaporization is the energy to shift 1 kilogram of substance from a liquid to a gas without a change in temperature. This is to completely break out the intermolecular bonds between those substances. We can see the slight differences in latent heats. We can see, I'll change to the laser, we can see the latent heat of fusion of water is this value here. The latent heat of fusion for water is this value. You can see the latent heat is generally higher for the transition of solid to liquid for the most metals, while as the latent heat of vaporization is a much higher value as well. So it actually takes more energy to break off the bond completely than it is just to cause it to have a minor gap separation. So that's why the latent heat of vaporization is much higher. The formula we use to represent the energy required for that separation is known, it can be represented by this equation here. So the latent heat is the energy required to change the state, liquid to solids, solid to liquid, liquid to gas, without changing temperature. So this is the formula we have here. M represents the mass in kilograms, capital Q represents energy in joules, and L is the specific latent heat. So that's a constant value based on whatever material you use. Okay? In any exam question, they would just give you that value, so not to worry if you're not sure where to apply it. Let's try a couple of questions. Question 1, how much energy must be removed from water, which has 2.5 liters, when there is a latent heat of fusion at 0 degrees to produce a block of ice at 0 degrees Celsius there. Okay, so this one is just a simple substitution. We're using 2.5 kilograms. We're using 3.34 to the 5, 10 to the 5 joules per kilogram. So plug that into the calculator. And we get our value in joules. If we want to convert this into kilojoules, 1000 joules equals to 1 kilojoule, so it will be 835 kilojoules there. Okay, question 2, we have a 50 milliliter of water, a vaporization of this value here, heat it from room temperature there to there. It is boiled at this temperature until it's completely evaporated. How much energy in total was required to raise the temperature and boil the water? So there's actually two components to this. Firstly, you need to work out the temperature change that we've implemented. So our formula here, we've used 50 milliliters, so that's equivalent to 50 grams. Okay, convert that in. We know what the specific heat capacity value is of water, and then we know we have a change of 80 degrees. Okay, and we also need to consider our latent heat. So we have the exact same mass, and then we have the vaporization. Okay, so let's look at what the two values are. So we have 16,800 joules, and we have 112,500 joules. So add those two together, and we've used up approximately 129,300 joules all together. Okay, next question we have is for the latent heat. Energy supplied at a uniform rate to a 400 grams of ice at 0 degrees Celsius. It melts totally in 5 minutes. If the latent heat of fusion of ice is this value here, we have a heat capacity of this here. The latent heat of vaporization is this value here. The total energy required to melt the ice firstly, what is that? Well, in this case, it will simply be the mass we have, so 400 grams, convert it into kilograms, times the latent heat of fusion. As you can see here, this is in kilojoules, but we can just leave it as it is for now. because we have the correct values for kilograms. So we've used a total of 133.6 kilojoules of energy to melt the ice. The next question is how much power, at what rate was the energy supplied to cause the ice to melt? Okay, so the total energy we used up is 133.6 kilojoules within a time frame of 5 minutes. So let's convert that into seconds. So 5 times 60. So we have a power rating of approximately, if we do it to 3 sig figs, 0.445 kilojoules per second. Okay, if we want to do it joules per second, it'd be 445 joules per second. What's the additional energy need to raise the temperature of water to 100 degrees Celsius? So again, if we're dealing with 400 grams of water with a specific heat capacity of 4,200, in this case, I'm just making that in joules because that's the number I'm used to. And the change in temperature, which is 100, and then plug that into our equation again and see what we get. That's 16,168.00 joules. Okay, it's done. How long will it take if the energy is supplied at the same rate? So if this is the rate we're using, okay, so 445 joules per second, the time it takes would be, so the time would be energy divided by the overall power. We have an energy total of this value here, and we have a power being used up per second of that. So it'll take about 378 if we round it off to 3 sig fig seconds. Okay, what's the additional energy required to evaporate the water? Now we are running out of space a little bit here, so I might just show this last one. Well, actually, let's just show you the response to this one, because you have seen the template of how to do B and C in with E and F here. So with E, we simply use the latent heat of vaporization. Again, convert the mass of water into kilograms and then times by the latent heat of vaporization. That's our overall value in kilojoules. Okay, and then what we have to find the time, you'll find that it takes about 2029 or 2030 seconds, so about 34 minutes to cause this vaporization or complete vaporization of water from liquid and making it into a vapor. Okay, so that concludes our lesson today about latent heat. We've looked at how latent heat comes into play when we are causing a temperature or heat transfer in an object, and we see how in our energy diagrams that when we have a latent heat or a transition between phases, there is no change in temperature because all that energy is being used up to cause the particles to separate from each other. If you like this lesson, please give it a like and obviously subscribe if you haven't already. Hopefully you have continued to enjoy the concept of thermodynamics. Until next time, take care.